So we are going to look at the concept of polarity and other forces that hold atoms together. So bonding between atoms of different elements is rarely purely ionic or purely covalent. This is where it's not black or white, it's more gray area stuff. So bond polarity deals with the electronegativity of atoms. And remember that electronegativity is the ability of an atom to attract electrons when it is in a compound. This is your electronegativity chart. I will supply that for you come quizzes or tests because there's no real pattern to memorize on this chart, and so this will be provided to you. And we've talked about electronegativity before, but the degree to which the bond is either ionic or covalent can be calculated by subtracting the electronegativities of the two atoms involved. So this chart along here, this gives you your kind of ranges of the different bonds. There are three types of bonds that we can have. You can either have mostly ionic bonds, and this will give you a difference in your electronegativities of 1.7 or greater. Okay, if it's 1.6982, that works as 1.7. Rounding is completely acceptable in this case. Polar covalent bonds have an electronegativity difference of either 0.4 to 1.7. And then mostly covalent bonds will have a difference in electronegativities of 0.4 or smaller. So ionic bonds, we've talked about, there's no differentiation. It's either ionic or covalent up until now. But now we need to kind of talk about the two different types of covalent bonds. And so the first one is called non-polar covalent bonds. And a non-polar covalent bond is a covalent bond in which the bonding electrons are shared equally. This means that the distribution of electrical charge is balanced between the two atoms. This occurs in diatomic molecules of hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And on the next slide, we'll look at diagrams of both of these types of covalent bonds. A polar covalent bond is a covalent bond in which the atoms have an unequal attraction for electrons, so the sharing is unequal. We call these polar bonds, and we'll take a look at these on the next slide. All right, so here we have non-polar covalent bonds because both chlorine, both of those atoms have an electronegativity of 3.0. So when you take their difference, they have no difference. It's 0. So that means that the electrons, the valence electrons in this chlorine atom are evenly distributed to this chlorine atom, and the electrons in this chlorine atom stay around that chlorine atom. We're not having a greater pull of electrons to one chlorine than the other. Whereas here in this diagram, we have hydrogen and fluorine. And so we'll notice here a couple different symbols. First of all, this little squiggly looking thing is the Greek letter delta. And we read this phrase as partially positive. So when we see this, that indicates to us that something is partially negative.
Delta was a triangle.
Oh, you're right. It's not delta. It's Yeah, I think it is sigma, actually.
It said delta in the room.
It did say delta in the notes, but maybe that's the capital delta? I don't know my Greek letters, like, apparently.
There's capital and lowercase.
Yeah, in Greek letters, there's capital and lowercase. Okay, thank you. Anyways, so what this whole situation is indicating is that this hydrogen atom is partially positive because the one valence electron that hydrogen brings to a compound is going to be more attracted to this fluorine atom because fluorine is... Oh, this is the lowercase delta?
Yeah.
Okay, thank you. So it is delta, just lowercase. All right, so backing up now, this one valence electron from this hydrogen is going to be more pulled towards this fluorine atom because fluorine has a higher electronegativity than hydrogen does. This fluorine has the pull. It is stronger in this tug of war between hydrogen and fluorine for the electrons. So that leaves hydrogen with a slightly or partially positive charge because that electron that it brings to the bond isn't really near that hydrogen. And then the fluorine will become partially positive because it's kind of got this pull on the hydrogen's electron, so it's pulling it towards the fluorine, causing it to be slightly negative. This is a constant tug-of-war situation. Think of your more electronegative element as the one that is going to pull the electrons towards it in a bond. So when this happens, we can draw this symbol. The plus sign is indicating that this side or this element, hydrogen, is partially positive because the electron or electrons, depending on how many it has, are being pulled towards that other element. Does that make sense? Mm-hmm. So sometimes they'll draw this in a bubble diagram. This smaller area is indicating the partially positive because it is missing electrons. Whereas over on this side, it's slightly larger because there's more electrons in that space, causing it to expand. Does that make sense? Okay. So this right here is an example of your polar bond. So a polar bond will happen when your electronegativities are not same. Whereas nonpolar covalent bonds happen when your electronegativities are the same. All right, so let's practice this. So if you need to look back in your notes to the electronegativity chart, you will need to know your electronegativities in order to be successful on these problems. So which type of bond will form between each of the following pairs of atoms? When you're asked this, you now can't just determine if it's a metal and a non-metal bonding. I want to see your electronegativity calculation. Okay? So in this case, what is your electronegativity of carbon? 2.55. And the electronegativity of oxygen? 3.44. Now, when you set up this subtraction, set it up so you always get a positive number. It doesn't matter how it's listed in the problem. There's no formalities other than your delta EN must be positive. So in this case, we're going to go 3.44 minus 2.55, and we get a value of, I believe, 0.89. Okay? So then, looking back on this chart here, 0.89 falls in which of these ranges? The polar covalent. Very good. So when carbon and oxygen bond, it will create a polar bond. And I only need polar. You don't need to write polar covalent. So then looking at sodium. Sodium's electronegativity is what?
0.
Wow, 0.93, good. And nitrogen, 3.04. Set it up so that you get a positive number in the end, 3.04 minus 0.93, and you should get 2.11. Going back to the chart here for 2.11, and that should be in which range? The ionic. Very good. And last one for practice, we have boron. What is boron's electronegativity? 2.04. Hydrogen's is 2.20. So setting it up so we get a positive answer.
0.16.
Equals 0.16. Go back to your chart. And 0.16 falls into which one? Mostly covalent. So when you get mostly covalent, that also means nonpolar.
Is that what you want as nonpolar?
Yep, nonpolar.
So these should be the only three answers, right?
Correct. Yeah, so your three possibilities are either polar, ionic, or nonpolar. So kind of a way to think about these is that this polar covalent bond is kind of the in-between of an ionic and a nonpolar. Does that make sense? There's a little bit of charges going on because of the electronegativities, but not enough to produce ions. Any questions, Leroy, or you're pretty okay with this? Good? Okay. All right. That's all right. So when we look at these, if there is a polar bond, it is going to create a polar molecule. A polar molecule is which one end of the molecule is slightly positive, while the other end is slightly negative. This creates something called a dipole, so two poles. So here we get a partially positive end and a partially negative end. Which of these ends, either the partially positive or the partially negative, those are your two answer choices here, which one will be the more electronegative end? Yes, very good. So this is going to be your more electronegative end. So when something is not polar, it will have your positive and negatives mixed up, flip-flop, like shaken up in a bag, no orderly fashion to it. But if we want to polarize the object, we can apply an electric field either through electricity or magnets. And when we do that, we put a positive end and a negative end. And when we do that, the molecules in the substance will line up so that the opposites are attracting one another. So the partially negative ends of the molecules are going to line up with the positive current or the positive side of the magnet, while the partially positive ends of the molecules will line up with the negative part of the electric field. This is how we get your, that's how polarized sunglasses are created. So in the production of the glass or the plastic, they will apply a polarizing force to them, align the molecules, freeze them in that position, and create the lenses from that.
Yeah, I almost thought it was like just like something fake. They're just like, oh, these are polarized.
Yeah, no, it's a real thing. So the molecular geometry of a molecule will affect its polarity. So if we look at this particular compound, the dipoles, oxygen is the more electronegative element, so it's pulling the electrons away from the carbon. Do we understand these diagrams? We can read that? Okay. And then whereas the water, the more electronegative element is in the middle, and it is pulling the hydrogen's electrons towards it. So When we look at the water molecule, we could draw a partially what by the hydrogens? Partially positive, very good. And up by this oxygen, you could label that as partially negative, and then this this hydrogen, this second hydrogen would be what? Partially positive. Good. And so this would be another way of drawing it. Your nonpolar molecules, your polar molecules tend to have the charges. I don't even know what I was going to say. I lost it. Skip it. Let's move on. All right. So in addition to ionic bonds, polar covalent, and nonpolar covalent bonds, we also have other forces interacting in between molecules. And these are called intermolecular forces. And they are weaker than the ionic or either of the two covalent bonds. There's really three, which I believe is on the next slide, the third one. The first one is called van der Waals forces. This is the weakest of the three, and it consists of dipole-dipole forces and dispersion forces. A dipole-dipole force is the attractive forces that occur between polar molecules. So that means molecules will align themselves so that the oppositely charged regions of neighboring molecules are near each other. So see here, this chlorine is partially negative, so it's going to align itself with this partially positive hydrogen. It's really just the opposites attracting one another. Okay? Your London dispersion forces are intermolecular forces that occur between all atoms and molecules due to the random motion of electrons. So, for example, the electron cloud of the helium atom will contain 2 electrons because helium has 2 valence electrons. And when averaged over time, these electrons will distribute themselves evenly around the nucleus. However, at any given moment, the electron distribution may be uneven, resulting in an instantaneous dipole, which only lasts for that instant, but it is still present. The strength of dispersion forces increases as the total number of electrons in an atom or nonpolar molecule increases. So that means oxygen will have a stronger dispersion force than nitrogen because oxygen has 8 electrons versus nitrogen's 7 electrons. Okay, so here quantity matters. Quantity of electrons matter. So kind of putting it into practice, if we look at this table, it's asking which halogen would then have the strongest dispersion force. So these are all halogens. So which one of these is going to have the strongest dispersion force? Cora?
Iodine does the most.
Yeah, good. Iodine will because it has the most electrons. So what would you say the relationship between dispersion forces and boiling points are?
The stronger the dispersion force, the higher the boiling point.
Stronger the dispersion force, the higher the boiling point. Why would that be?
The chart.
Okay, so yeah, the numbers say that, but molecularly, what happens when you boil a substance? It doesn't necessarily.
The molecules don't break down, but they come apart.
They come apart, so what's coming apart?
I don't know. The bonds.
The bonds or the forces between the molecules. So when you're boiling it or going from a liquid to a gas, you're breaking down those intermolecular forces, and if there's more intermolecular force, you're going to need more energy or a higher temperature to break them apart. Does that make sense?
So basically, wait, never mind.
All right then. Hydrogen bonding is an intermolecular attractive force in which a hydrogen atom is covalently bonded to a small, highly electronegative atom, and it is attracted to a lone pair of electrons on an atom of a neighboring molecule. This is your strongest intermolecular force. So it's stronger than dipole-dipole, it's stronger than London dispersion. It is the strongest. However, it's only 5% as strong as a covalent bond. So again, your ionic and covalent bonds are going to be stronger than these hydrogen bonds. Hydrogen bonds will only occur if your hydrogen is bonded to these three atoms: fluorine, oxygen, or nitrogen. So water has hydrogen bonds because hydrogen is bonded to an oxygen. So when hydrogen molecules are placed near one another, this oxygen is going to be attracted to this hydrogen because this oxygen is partially negative. And we kind of know that already because if we look at this, there's really two unbonded pairs of electrons on that oxygen. Does that make sense? So that automatically is going to make this oxygen partially negative, and it's going to attract a partially positive end of another molecule. Okay? So that leads us to some very important things about water. So in the liquid state, hydrogen bonds break down and reform as molecules flow from one place to another. So every time you move liquid water, you are breaking and reforming hydrogen bonds. This is what allows water to flow when you pour it from one container to another, when you slurp it up a straw, as it is moving through your body. It is constantly breaking those hydrogen bonds and then reforming them. When water is cooled, the molecules begin to slow down and will eventually freeze in place. This makes the hydrogen bonds very rigid, not frigid. And so this we'll talk about in this next bullet. The bent molecular geometry of water will create gaps in the hydrogen bonding network of ice. So on the next slide, we'll see a diagram of this. It makes it less dense than liquid water because there's a bunch of air pockets, microscopic air pockets between all of the hydrogen bonding. This is highly unusual to have a solid that is less dense than its liquid counterpart. So if we look at this, the red would be the oxygen or the oxygen atoms, and the white is the hydrogen atoms. And so the dashed lines represent the hydrogen bonds. But notice, because of the bent structure of a water molecule, it leaves all of this empty space. And this empty space is filled with air then, which causes ice to be less dense than water. All right, 2 slides left. Boiling points and bonding types. If a substance is in the gaseous phase, the particles must overcome the intermolecular forces holding them together, which we talked about on the other slide where we had the iodine having the greatest intermolecular forces. So this is your order of strength right here. London dispersion forces are weaker than dipole-dipole, which are then weaker than hydrogen bonding. So if you're ever asked which is your strongest, you would say hydrogen. Good. And then the last kind of exception to these rules is if the mass of the nonpolar molecule is large enough, its dispersion forces can be stronger than the dipole-dipole forces than in a lighter polar molecule. So a little bit that size matters again. And then molecular and ionic compounds. The physical state and properties of a compound will depend largely on the type of bonding within the molecule. And so here is a comparison chart of ionic and molecular compounds. It shows you the types of elements, the types of bonding that can occur, what we call the representative unit. So a molecule is a single unit of a molecular compound, where a formula unit is the individual component of an ionic compound. The physical state, so is it a solid, liquid, or gas at room temperature? Room temperature sits right around 23 degrees Celsius, I believe. Yeah, I think so. Water solubility, this means that it is soluble in water, aka water dissolves it. The melting point and boiling point temperatures, if you have an ionic compound, it will generally have a high boiling point. That means you need lots of energy to break down those bonds and intermolecular forces, where molecular compounds will generally have a lower boiling point and melting point because you don't need as much energy. And electroconductivity, ionic compounds tend to conduct electricity if they're melted or in solution, where molecular compounds do not.